Hi, everyone. Ashkan and I will be co-presenting this presentation today. So I'll start us off with the motivation slide. My name is Janani, and what I'm going to talk about today is signal and power integrity co-simulation methodologies and why they are important for high-speed parallel interfaces. So basically, as everyone in this room knows, we have recent advancements in signal and single-ended signaling for memory interfaces, LP and DDR4, 4x5, and one of the main advantages of going to these different interfaces is that you are able to operate at higher speeds, but you also have to have power savings, so you have to operate these interfaces at lower voltages. So these opposing trends of higher speeds and lower voltages actually shrinks the I margin that is available for a channel to be properly sampled at the receiver. And as shown here is just a sample DDR4 system timing margin window at the RX pin that just shows that in order to meet your setup and hold times, you have a certain opening, and this is shrinking because of lowered voltages and at higher speeds with UI also shrinking. What we're showing here is that we have to design not for SI and PI separately, but for performing a co-simulation where we can see the impact of power noise on jitter and how it actually, interacts with the signal integrity simulations. So to this end, we've used Synopsys PrimeSim 8-Spice, and we've leveraged it to implement these simulation techniques. These techniques are quite popular in the industry, have been for many, many years. I could even say more than a decade and a half, to predict like the power supply noise impact. But how it is still relevant today in the higher speed interfaces is because of shrinking margins, where we cannot split the simulations and do separated budgeting for SI and PI. So shown here are some graphs of the LPDDR voltage trends and the evolution of the LPDDR speeds, and also shown here are the shrinking VDDQs. With this motivation slide, I'm going to hand it off to Ashkan, my colleague, and he'll talk a little bit more about the methodology.
Good evening, everyone. So I think for all the reasons that just Janani mentioned, co-SI PI and simulation PI with SI together would be critical for this especially parallel interface as we lower down in the voltage, and also we kind of shrink the margins. So as you know, there are quite few techniques that you would include both SI and PI in your simulations, but this one that I'm going to describe here may be more efficient way if you are dealing with kind of larger scale system that you would like to still have kind of transistor level accuracy in the simulations. So you kind of, obviously when you're doing SI-PI, you would like to include all your SI and PI components that go into your system analysis. And I'll, in the next slide, briefly cover on the kind of analysis that you use in order to model your passive structure. But assuming that you start with your transmitter, and then going to if you have any on-die routing, interposer, or any passive structure that you might have as your packaging solution, all the way to the receiver. So if you have basically put together your system, it's essentially kind of computationally prohibitive if you would just want to have all the transistor level models in your design and then have run the system. Let's say in this case, if you're dealing with the 24 IO tiles, that we are including the transistor level models in there. So it's kind of impossible to have every driver model. So one technique that can mitigate this problem is using the current mirrors, which is widely being used in the industry. And what it does, essentially, you want to have your transistor level models of your actual drivers and the aggressors that kind of surrounding your victim. And you use current mirror in order to, first of all, you start to measure the current consumptions of the actual drivers that you use for your system, and then try to scale that in order to mimic and represent the SSN drivers of your system. So once you have that kind of current mirror setup and your actual drivers in the system, you can actually run 3 different sets of tests, where you can start with your ISI only test. And what it means that you just start toggling your victim as the actual driver model with the transistor level models. And then also the surrounding aggressor, you keep them quiet with the SSN drivers. So whatever you get from this kind of test, you'll understand that that would be your kind of contribution of your ISR into your final, timing budget. And then in the next set of tests that you create, you start to bring your ISI, your crosstalk aggressors, which surrounding your, victim. In that case, you kind of start to bring the effect of crosstalk as kind of in addition to your ISI, and that can individually can budget your crosstalk plus ISI effect into the overall link performance. And eventually, once you have those, you start to bring your SSN drivers. These are the current mirrors that you already in the actual simulations you measured and scaled. And now you're putting them and start toggling them in order to, in this case, excite the worst case PDN. And usually the worst case PDN that you want to excite in this case is that you want to have a kind of burst, idle burst pattern. And that frequency or period between those bursts and ideal pattern, you want to be that kind of coincide to your PDN resonance frequency. So if you try to kind of mimic that kind of pattern, you're kind of assuring that you're, exciting your worst case PDN or SSM pattern on top of your ISI and, crosstalk effects. So that's kind of the methodology. But part of the system or subsystem that goes into this is essentially how you define your, passive channel as well as your PDN. So obviously, because of the type of the structures like 3D or 2.5D that we're dealing with, you might consider to have like a horizontal kind of model on the lateral routing of your packet. And also you will be dealing with some, vertical routing depending on if you're using like interposer or any 2.5D or 3D IC structures. So ideally, you would like to have a kind of 3D EM simulation for your vertical path, as opposed to in the lateral or horizontal paths. You could also have some techniques or 2D or 2.5D that kind of reduces the complexity of the computation. But as you are dealing with like smaller pitch and high density environments, you would like to have a kind of tool or methodology to, once you're not only you're looking at the signal to signal interaction, but also you want to kind of quantify how your power and signal are interacting with each other. So that's kind of the strategy that you would like to have when you're trying to model your horizontal and vertical channels. And then when it comes to the PDN, as much as detail that you can get into your PDN model will help in this kind of techniques. So it's best to have a kind of segmentized approach where you kind of model your chip and silicon decoupling scheme if you have any model from your vendors, or it's like internally developed like CPM models, or if you are getting any decoupling schemes from the manufacturer, like you can add any MEM or MOM capacitance from the foundry. You also want to include all of those, and then going all the way to the package and the board. And one thing that if you're going to basically strategize this PDN is that this kind of analysis gives you the ability to kind of do what-if analysis, meaning that you kind of eventually you're connecting this whole PDN to the pad of your transistor when you're using the transistor level models. So that gives you the ability to do what-if analysis. Let's say if you're doing a design space exploration at the package level, so you should be able to kind of do sweeping the parameters or the package in order to find out your worst case package. So that gives you kind of a knob in order to make sure that you are, if you are going to design for the worst case, you're actually having the worst case, or if you're kind of tight on the budget, you want to be closer to the, the reality once you see in the lab, then you also want to make it closer to that kind of package scenario. So this is, how detailed that you could basically go in terms of, channel and PDN model that goes to that, the full system level analysis. And once now you set up your, channel model, you already know your PDN and you already set up your current mirrors and everything. So you have the full, system end-to-end ready to run. One kind of criteria or kind of pre-characterization step that you could do is to kind of do a step analysis in order to find out how much each individual components is actually impacting your actual link. And it's helpful because, let's say we're at the design stage, we want to kind of decide how many a crosstalk aggressor I need to include into, my system analysis. It could be maybe like the first adjacent, like 3 aggressors or the 5 or the 6. And also, what is the optimum number of SSN, aggressors I need to apply into my system? By doing the step analysis, for example, in the, the black one here, is showing that if I'm just enabling the crosstalk only in, aggressors, I'm getting like 40 millivolt in terms of peak-to-peak noise that I can get in the step. And then by moving or kind of changing around these numbers, I should be able to find a sweet spot in order to find out how many current mirrors I need to put into my system. Let's say if I'm getting 40 millivolt for 6 crosstalk, if I do it like 8, probably I get like 41 millivolts. So that's the kind of criteria telling me, okay, maybe 6 number of crosstalk aggressor is what I want to have my system. And then I use the remaining drivers into my system as the SSN excitation to kind of excite the worst case SSN. And then eventually all of these will kind of translate into the eye diagrams that you get at the end in the transistor level simulation. So this also can enable you in order to find out the impact of each individual component to the overall link budget. Let's say if I'm looking at only ISI versus ISI crosstalk and then crosstalk plus SSN, you can see from the eye diagram and also the budget, if I'm not including a SSN effect into the whole link, probably I'm losing like 2% UI of my margin. And as as we go to the higher frequency, this kind of be very close to the timing budget that basically you're assigning for your link. This is another example for LP5. We just put this together as a kind of example to kind of signifies the same thing that we just discussed. Intentionally, we're picking like a worst case channel, kind of worst case package and the PVT corners, and not using any equalizations or package decoupling to kind of show the significance of including or not including SSL into that interface. And again, as expected, if you look at the kind of brown eye diagram here, it's just showing the ISI. Obviously, it just looks like a kind of ideal eye. But as you start to include, your crosstalk and SSN aggressor, that's what you start getting, the black and the red curves. So that meaning that by including those, aggressors, you kind of start seeing the exact effect into your final eye. And the graph on the right is just kind of confirming what you just mentioned. That's showing the power noise at the, the power, the PDN pad that you connect at your transistor. And if you baseline, the ISI only case, you can see as soon as we start to have the SSN drivers toggling at the worst case PDN, you see the amount of noise is kind of increased compared to what if you're including only crosstalk aggressors. And that's basically shown in both, eye diagrams and also the power noise. I think I'll hand it over back to Janani to just go on another case study that we have here.
Thank you. Thank you, Ashkan. So Ashkan introduced the details of the SIPI co-simulation approach and showed 2 examples, one with a custom I/O channel and another with an LP5 channel. What I'm here to show is one of the ways you can, the SIPI co-simulation method, can be applied is in picking actually your PDN scheme and like the decoupling capacitors that are effective in channel performance. So I think for PI engineers, you're very used to picking, on-package decoupling or on-board decoupling in order to meet a certain noise budget that is a percentage of your VNorm. But instead of just meeting a noise budget that's a percentage of your VNorm, if you could actually see the impact of that voltage noise on the eye, which ultimately is what you're trying to design the system for, that's where the usefulness of the SIPI co-simulation method really comes. And that's the power of actually the co-simulation approach, where like what Ashkan said, you have to model the channel in a reasonably accurate manner. You have to pick the exact number of aggressors. And in this specific case, what we did was, in the PDN, unlike the previous examples, we had a study of whether we placed package decoupling above the package core or the package code in this specific sample package, the code was quite thick as it is in data center packages. And between OPD option 1 and 2, we could actually run test cases and do an apples to apples comparison to see, okay, what is the percentage contribution from SSO noise that would need to meet the budget at the end of the link. So here, of course, another advantage of using an SIPI co-simulation method is you can model the PDN actually in a partial manner, because as you know, when you run simulations in EDA tools, you get S parameters. And S parameters typically loop both your power and ground into the ports. And if you plug those S parameters into your SIPI co-simulation methods, all of the power noise would actually show up on the power side, and it would be asymmetrically very small on the ground side. But in reality, if you actually measured this in the lab, you would see that there is significant amount of ground bounce as well. It's not as much as power, but there is also some on the ground. So that is another advantage of using the SIPI co-simulation method, is you can actually model it in a peak method where you do partial PDN models, do something like an OPD option 1 versus 2, and actually show the impact on the SSO noise as it was done for this paper a few years back. So we've talked a lot about SIPI co-simulation. We've shown about 3 test cases where we have used this successfully in our designs. But there are certain caveats to using this methodology. You do need SPICE models. You don't need accurate circuit models, because you need to be able to simulate the power noise that is actually taken from the PDN network by the driver that you're using. So you will need a transistor level driver in order to capture the power noise. In the absence of that, you could use IBIS AMI, as some of our the presenters before us have demonstrated, to also capture that noise effect. And in many cases, if you work with vendors, you might get only IBIS models, which don't provide this advantage of actually modeling, capturing the voltage noise and its impact to the IV curve. The other caveat is that because you're applying current mirrors on the power delivery network, if you do not have a reasonably distributed power delivery network on die, you're artificially applying all the current on a single node, and that could also provide simulation results that are artificially large. So you do need an detailed on-die SPICE-like network to capture the distributed nature of the PDN, and also in some cases help filter out the impact of the noise to the victim driver. So in the absence of the models, let's say you don't get these models from your vendors, then the alternative that has been traditionally used is you run SI only jitter performance, which is you would run get an IBIS model, or even with a transistor model or with a behavioral model, just traditionally separate the SI simulations out. You would capture PDN noise separately, like you would as a certain percentage of V norm. But the con of this is pessimistic budgeting, which at these type of speeds for LP5 can be challenging. And there's also a question of current profile accuracy, because when you simulate the power noise separately away from the actual transistor circuit, you do not know how the current draw from the PDN changes with the voltage that is applied to the power node on your transistor. So that IV relationship is kind of static if you just take a current profile out and apply it to a PDN. So those are the caveats that we have to keep in mind while we're doing the SI only and PI only jitter, which is why we kind of recommend doing the SI, PI simulation, co-simulation together. But there are sometimes you cannot escape it. And Ashkan is here to show one such example for LP4, where we did only an SI only simulation and its impacts.
Yeah, I think we are running out of time, so I'll make it quick. So this is basically just showing that there will be a case that basically we as a channel designer, you're supposed to just design a channel that you might not really be aware of what kind of models that you're going to get from your RX or TX. So you're kind of in an environment that you would like to kind of stress test your channel, but at the same time, in the future, you want to make sure that it's going to work with different kind of mix and match of driver and receiver. So one technique that's basically is explained in this paper is that you could actually define a kind of reasonable worst case with kind of stress your eye at the receiver side. So let's say if we pick, the DDR interface, and then we kind of JEDEC specs, like what would be the worst kind of, let's say, input capacitance for the RX, you pick that one. And then you also have some TX kind of input that you would get from your vendor. May not be a model, but just kind of jitter number or rise sample. You kind of do a mix and match of those environments to make that a stress eye. And as long as your channel that you design is going to be kind of passing that specific, stressed eye, you kind of can assure that, okay, you're not idealistically, but you are at a good starting point. So you can start with that as your channel design. And once you're getting the models, you kind of start to bring in the accurate models. It could be, IBS, IBS-AMI, or like the transistor level that we discussed earlier. So that would be a kind of angle that we would like to highlight here, that those models, if not ready, there are some techniques that you kind of stress your eye and then try to design for that stressed eye. And I think with that, I'll turn it back to Janani to just wrap up the session.
Thank you. Yeah, I think we covered a lot of the techniques in detail here. So I'll just leave you with the key takeaways here. SIPI co-simulation can be a powerful methodology. It has been used in the industry before, but I think it's still relevant for the speeds that we are operating the parallel I/O interfaces today. We've shown several case studies using custom IOs, DDR4, LPDDR4, and 5 that show the capability of this. But there are limitations to the methodology, as there is with any methodology, and that has also been investigated and should be kept in mind when we are applying this. For all of these, I think the key is using a SPICE-like simulator because it can capture very detailed RLGC networks. It can combine S-parameter files for your channels with your RLGC networks, and it's useful for scaling designs to the number of IOs that we have in all these parallel interfaces. So with that, I'll conclude. Thank you.